We are going to solve a classic physics challenge. Find the moment of inertia of a uniform thin rod when the axis is moved from the center to one of the ends. This is where the parallel axis theorem shines, and we're going to see it step by step. The parallel axis theorem tells us that the moment of inertia about any new axis parallel to the center axis is equal to the moment of inertia about the center plus the total mass times the square of the distance between the axes. Written out, I equals I center of mass plus md squared. We already know the moment of inertia of the rod about its center, 1/12 ml squared. This is our I center of mass term that will be plugged into the theorem. The distance d between the original axis at the center and the new axis at the end is half the length of the rod, so d equals L/2. We'll square this value next when we plug it into the theorem. Now let's substitute I center of mass and d into the formula. We get I equals 1/12 ml squared plus m times L/2 squared. Now add the fractions. 1/12 plus 1/4 gives 4/12, so the entire expression becomes 1/3 ml squared. This is the moment of inertia about the axis running through one end. So there you have it. The rod's moment of inertia about an axis through one end is 1/3 ml squared. The parallel axis theorem gave us a swift way to shift the axis away from the center. Problem about a solid disk rotating when we push on its rim. We'll look at torque, then angular acceleration, and finally the angular velocity after a few seconds. We have a uniform solid disk with 4 kilograms mass and a radius of half a meter. A tangential force of 12 newtons acts on the outer rim, just like pushing on the edge of a wheel. This creates a torque that starts the disk spinning. Step 1. Calculate the torque. Torque is force times the lever arm. Since the force is tangent to the rim, the lever arm equals the radius half a meter. So tau equals 12 times 0.5, which is 6 Newton meters. Step 2. Find the angular acceleration. First, we need the moment of inertia for a solid disk, which is half m r squared. Plug in 4 kilograms and half a meter. The result is 0.5 kilogram meter squared. Then use tau equals I times alpha. So alpha is tau divided by I. That gives 12 radians per second squared. Step 3. Find the angular velocity after 3 seconds. We start from rest, so initial omega is 0. Use the kinematic equation omega equals omega naught plus alpha times time. So omega equals 12 times 3. After 3 seconds, the disk spins at 36 radians per second. In summary, pushing tangentially on a disk gives us 6 Newton meters of torque, which causes 12 radians per second squared of angular acceleration. And after 3 seconds, the disk spins at 36 radians per second. That illustrates conservation of angular momentum. Imagine a skater spinning with her arms extended, and then pulling them close to her body. What happens to the spin rate, and how does the energy change? Let's draw the skater twice, once with arms extended and once with arms tucked in. We want to highlight that angular momentum stays the same, so speed changes. We use conservation of angular momentum. I sub 1 omega sub 1 equals I sub 2 omega sub 2. Now plug in the known numbers to solve for omega sub 2. Next, we compute rotational kinetic energy before and after the arms move in. K equals 1/2 I omega squared. The energy increased from 28 joules to 70 joules because the skater does work to pull her arms in. Her muscles push inward, converting chemical energy into extra rotational kinetic energy, while angular momentum stays constant. Exploring how a solid sphere rolling without slipping converts all its initial potential energy into motion. This is an intuition-driven approach using conservation of mechanical energy. Our scenario: a solid sphere of mass m and radius r sits at the top of a frictional-free incline of height h and starts from rest. Let's draw the physical picture. We have an incline, the sphere sits at height h, and it rolls down without slipping. We mark the radius r and show how the sphere rotates while it travels down the incline. At the top, the sphere is at rest, so all of its energy is gravitational potential energy, mgh. At the bottom, the height is 0, so energy is purely kinetic. Rolling motion has both linear kinetic energy 1/2 mv squared and rotational kinetic energy 1/2 I omega squared. Finally, combining terms, the rolling kinetic energy becomes 7/10 mv squared, which we equate to the initial potential energy to find the final velocity. When we cancel our squared, the rotational term becomes 1/5 mv squared. Adding that to the linear part gives 7/10 mv squared for the total kinetic energy at the bottom. Conservation of energy says potential energy equals kinetic energy at the bottom. So mgh equals 7/10 mv squared. Mass cancels out on both sides. Divide both sides by 7/10 m, cancel mass. We then multiply by 10/7 and take the square root, giving v equals the square root of 10/7 times gh. So the clean answer is the linear velocity at the bottom is the square root of 10/7 gh. All of the potential energy has become motion, split between translation and rotation for the rolling sphere. Radius r equals 0.2 meters. A block of mass m equals 1.0 kilograms is attached to the free end of the string and allowed to fall vertically under gravity. Assuming the pulley rotates smoothly without friction about its central horizontal axis, and the string does not slip, let's draw the physical system. First, let's draw the free body diagram for the block. Next, draw the free body diagram for the pulley. For the block, Newton's second law gives mg minus t equals m times a. For the pulley, the torque tau equals the moment of inertia I times the angular acceleration alpha. The torque from the tension is T times R. The moment of inertia of a solid cylinder is 1/2 m r squared. And alpha equals I over R because the string does not slip. Substituting those expressions into the torque equation and canceling and R gives T equals 1/2 ma. Now substitute the expression for T into the block equation mg minus T equals ma. Collect the terms. mg equals ma plus 1/2 ma, which is m plus 1/2 m times a, dividing through equals mg divided by m plus 1/2 m. Calculating the denominator, 1 plus 1.0 is 2.0. Dividing 9.8 by 2.0 gives 4.9. Thus, the acceleration is 4.9 meters per second squared. Calculating the denominator, 1 plus 1.0 is 2.0. Dividing 9.8 by 2.0 gives 4.9. Thus, the acceleration is 4.9 meters per second squared. So the block falls with an acceleration of 4.9 meters per second squared. That's the answer.